Welcome to the online course on pericyclic reactions and organic photochemistry. We are in the fourth week of this program. We will have 5 modules in this week, and in all the 5 modules, we will consider a very important reaction called the sigmatropic rearrangement reaction. Now, sigmatropic rearrangement reactions are defined as reactions involving a breaking of a sigma bond with the migration of a group or atom that is originally connected to the sigma bond over a conjugated pi system, resulting in the formation of a new sigma bond with the concomitant reorganization of the pi electrons. This may be difficult to follow without an example. We'll straight away go into an example in the next slide. What is important here is that the breaking of the sigma bond and the reorganization of the pi cloud, everything takes place simultaneously in a concerted manner. The order of the sigmatropic rearrangement is indicated by 2 numbers within a square bracket. Now let us take this example shown in equation number 1. The equation number 1, it is a simple allyl system to which a functional group or an alkyl group is connected, which is the R group. The thick bond that is shown here is the bond that is going to break, and with the breakage of this bond, the R group migrates to the third position. In other words, the numbering starts from the bond breaking during the course of the sigmatropic rearrangement. If the carbon R bond is breaking, then the numbering starts from 1 and 1, and the migration takes the R group to position 3. So it is a 1,3 R shift. Let us say, for example, if the R is a hydrogen, then it will be a 1,3 hydrogen shift. If R is a methyl group, then it will be a 1,3 methyl shift. If R is a generally an alkyl group, then it will be 1,3 alkyl shift is what we are referring to. During the course of the migration of the R group to the third position, the pi bond automatically reorganizes so that the overall process is a concerted process without involvement of any kind of radical species or any intermediate species. The same analogy can be extended to a 1,5 shift. This is a butadienyl system to which a carbon R group is attached. This carbon is a saturated carbon, sp3 carbon. The group is now migrating to position number 5, so it is a 1,5 sigmatropic rearrangement. Now these are 2 special class of sigmatropic rearrangement where the thick bond that is shown here is migrating, and during the course of the migration a new bond is formed between carbon number 3 and 3. These are called 3,3 sigmatropic rearrangement. There is a special name for this reaction. It is called the Cope rearrangement. Now the second reaction example that is shown in equation number 4 is nothing but an oxygen analog or a heteroatom analog. It could be oxygen or nitrogen. And if it is the oxygen, if X is equal to oxygen, then the 3,3 sigmatropic rearrangement of this type is called Claisen rearrangement. Claisen rearrangement is nothing but a vinyl allyl ether undergoing a rearrangement to give alpha, beta, gamma, delta unsaturated carbonyl compound. So these are the generic examples of 3,3 sigmatropic rearrangement. Let us look into further classification of the sigmatropic rearrangement. In the equation number 5, an example of a 2,3 sigmatropic rearrangement is shown. Here the X and Y atoms can be either carbon atom or it could be heteroatom. In such a case, the carbon X bond cleaves and the new bond is formed between Y and the third position. So if you number the carbon X bond as 1 and 1, then it comes to 1, 2, 3, here 1 and 2, and the 2 and 3 are connected, so it is called a 2,3 sigmatropic rearrangement. Here is an extended example of the same reaction. This is a 3,5 sigmatropic rearrangement. You can see here the carbon X bond is being broken, and if that is a broken bond, then the numbering starts from 1, 2, 3, 4, 5 on the lower side, 1, 2, 3 on the upper side. The new bond is formed between 3 and 5. As you can see here, this is a new bond that is formed. So it is a 3,5 sigmatropic rearrangement. This reaction is known as benzidine rearrangement when X group is a nitrogen or NH, for example. The NH-NH bond in benzidine is broken under strongly acidic condition due to protonation. Under these conditions, the para positions are connected by a sigma bond through a transition state of this type where the 2 benzene rings are parallel to each other, for example. And the 5,5 bond is the 5 by carbon is what is attached during the sigmatropic rearrangement, and that is corresponding to the 5,5 sigmatropic rearrangement. Now let us see what are the modes by which the hydrogen migration can take place. Let us take the example of this particular pi framework where one can expect a 1,5 sigmatropic migration to take place. It is a hydrogen atom that is going to migrate from this position to the position where R3 and R4 groups are attached with a concomitant rearrangement of the pi bonds to the corresponding adjacent position. Now in doing so, the hydrogen can migrate from the top phase to the top phase of the pi framework. This is called the suprafacial mode. In other words, suprafacial essentially means from the same side or from the same phase. Now we are talking about the pi phase. Hydrogen doesn't have any suprafacial or anterofacial migration, but with respect to the pi phase, it can either migrate to the same position from the top phase to the top phase, or from the top phase it can go to the bottom phase also. Such a migration would be called an anterofacial migration. So if a suprafacial migration takes place, this would be the configuration of the resulting chiral center that is generated. If an anterofacial migration takes place, this would be the configuration of the resulting migration center that is taking place. In the above example, supra and antra are with respect to the pi phases only because hydrogen doesn't have any suprafacial or anterofacial modes of migration. On the other hand, if we consider carbon, carbon can have suprafacial or anterofacial migration depending upon whether the migration takes place from the breaking of the carbon-carbon bond, which is shifted onto this position, or breaking of the carbon-carbon bond with the inversion of configuration in an anterofacial manner. Now let us take this particular example where it is with respect to the pi phase suprafacial and with respect to sigma phase also suprafacial. This is equivalent to breaking this bond, carrying this R1, R2 and R3 groups and migrating it with intact to the other position from the top phase itself, such that the R2, R1 and R3 groups are, let us say, having the same configuration in the starting point as well as in the end point. On the other hand, if the R group were to invert and migrate in this position, in other words, the lobe on this carbon is going to interact with the backside lobe of the carbon which is undergoing the migration. Such a migration would result in the inversion of stereochemistry because it is equivalent to an SN2 type of an attack to the rear side of this particular carbon. So you can see here the configuration here R1 and R2, R3 are in the clockwise direction, in the anti-clockwise direction, whereas R1, R2, R3 are in the clockwise direction in this particular manner. So whenever a sigmatropic rearrangement takes place in an anterofacial manner with respect to the sigma bond that is being broken, then the inversion of stereochemistry is what is expected in this case. In the top example, with respect to the pi system, it is suprafacial. With respect to the sigma system, sigma in the sense the carbon-carbon bond that we are referring to as a sigma system. With respect to that, it's sigma suprafacial on the left hand side, sigma anterofacial on the right hand side. Now let us take the bottom example. Similarly, one can have with respect to the pi anterofacial, in other words, the migration takes place in an anterofacial manner with respect to the pi framework. This carbon-carbon bond is above the pi system. Now if it migrates to below the pi system, in other words underneath the pi system, then it would correspond to an anterofacial migration with respect to the pi system. On the other hand, you can also have anterofacial migration with respect to the pi system, but a suprafacial migration with respect to the sigma. In other words, this bond is broken and it comes and attaches itself in this manner. You can also, in principle, can have an anterofacial migration, but in practice, such migrations are sterically and very cumbersome, so they do not take place in this manner at all. Now let us use the frontier molecular orbital methods of analysis for describing the 1,3 hydrogen shift and 1,3 carbon shift. Now if you look at this diagram, this essentially is a sigma bond connected to a carbon hydrogen bond is what is represented. Hydrogen, remember, is a 1s electron, so it is approximated to be a spherical density of electron in this position. And this is a pi system representing the LUMO of the pi system and the HOMO of the CH bond. When the migration takes place, the hydrogen can migrate in a suprafacial manner to this position, and that would essentially end up in an antibonding kind of an interaction in the thermal migration. So a thermal suprafacial 1,3 hydrogen shift would be a forbidden process under thermal condition. On the other hand, if the hydrogen migrates in an anterofacial manner, as it is shown here, To start with, it is a bonding interaction. To end up also, it is with a bonding interaction. So an antifacial 1,3 hydrogen migration under thermal condition is an allowed process. However, imagine a 1s electron density overlapping between carbon number 1 and carbon number 3 in an antifacial manner. This would be a geometry forbidden process. So although Woodward-Hoffmann says that the antifacial 1,3 hydrogen shift is an allowed process, it is seldom observed because of the fact that the 1s hydrogen orbital cannot overlap. It is not big enough to overlap, for example, with the 1 position and the 3 position of the carbon framework. On the other hand, if you consider a sigmatropic migration of a carbon-carbon bond, the carbon-carbon bond, the carbon which is migrating has 3 substituent A, B, C in an anti-clockwise direction configuration in this manner. When it undergoes a suprafacial migration, the configuration is retained. In other words, a 1,3 suprafacial shift retains the configuration. However, if you look at the diagram carefully, this is a suprafacial shift, but at the end of the interaction that you see here, this is a antibonding kind of an interaction. So this shift is essentially a forbidden shift as far as the thermal migration is concerned. On the other hand, if you consider an antifacial migration, in other words, this lobe here essentially interacts from the backside of this carbon-carbon bond, something like an SN2 kind of a process. So the lobe of the carbon essentially overlaps with the 1,3 positions of this pi framework, resulting in an antifacial migration with the inversion of stereochemistry at the migrating center. This is an allowed process with an inversion of stereochemistry. So a 1,3 carbon shift is allowed under the conditions of inversion of stereochemistry under thermal condition. One can extend the same analysis to a 1,5 hydrogen and a 1,5 carbon shift. In the case of a 1,5 hydrogen shift, it is easily allowed because it is a larger framework and it is a suprafacial migration also. So a 1,5 suprafacial migration of both the carbon as well as hydrogen are allowed under thermal condition. However, the antifacial migration is a forbidden process, as in the case of the migration leading to an antibonding type of an interaction in the transition state of this rearrangement. To summarize the Woodward-Hoffmann rule for 1n hydrogen shift, 1n hydrogen shift, because the hydrogen is a migrating group, there is no stereochemistry involved here. So if you consider a 4n electron system, in other words, systems involving 4n electrons, as in the case of 1,3, 1,7, in the case of 1,3, it will be 1 pi bond and 1 sigma bond. So 2 plus 2, 4 electrons are involved. In a 1,7 shift, it will be a triene and a CC bond. The triene will have 6 electrons and the CC bond 2 electrons. Totally 8 electrons would be involved in the reaction. So it is overall a 4n system. In the 4n system, under thermal conditions, at least one of the component has to be an antifacial component for it to be thermally allowed. If both of them are suprafacial, then it is forbidden process under the thermal condition. Under photochemical condition, it is the complementary nature of the Woodward-Hoffmann rule is reflected here. When one of the component is an antifacial component, it is forbidden. When both the components are suprafacial, then it is an allowed process. Now in the 4n plus 2 electron system, as in the case of the 1,5 sigmatropic rearrangement or a 3,3 sigmatropic rearrangement, both the components have to be suprafacial in nature for it to be allowed under the thermal condition. Whereas if one of the component is an antifacial component, it becomes forbidden under thermal condition. Of course, in the photochemical condition, the opposite is true. When both the systems are suprafacial with respect to each other, then it is forbidden. When one of the component is antifacial, then it is allowed for a 4n plus 2 kind of a system involving, let us say, for example, 2,3 rearrangement or 1,5 rearrangement or 3,3 rearrangement and so on. When carbon is involved in the sigmatropic migration, whenever you have an antifacial component of the carbon, whether it is allowed or disallowed, that is one thing that one need to worry about. When it is allowed, it will undergo inversion at the carbon center. That is extremely important, for example. So wherever you have a sigma antifacial allowed process taking place, it has to happen with the inversion of stereochemistry of the carbon that is undergoing the migration. We will see some examples of this kind of 3,3 sigmatropic rearrangement and understand it very clearly with respect to the inversion of stereochemistry during the course of the antifacial migration. One can also use transition state aromaticity method for the analysis of 1,3 shifts. If we consider a 1,3 shift of this type, it's a suprafacial shift. So the overlap is a continuous overlap of the 4 electrons that are involved here, resulting in a Huckel type of a transition state, which is anti-aromatic transition state. So anti-aromatic transition state in an antifacial manner would be this is a 1,3 superficial shift, for example, resulting in an anti-aromatic transition state. So it will be a forbidden transition state. On the other hand, if it is an antifacial migration, that will be a foreign electron system, Mobius kind of a system. And such a Mobius kind of a transition state will be an allowed process because it would be an aromatic transition state. So antifacial shift is allowed under thermal condition, whereas superficial shift is forbidden under the thermal condition. Exactly opposite is true for the case of the 1,5 shifts. If it is a 1,5 suprafacial shift, for example, it is a cyclic 6 electron transition state, which is a Huckel kind of a transition state. So it is aromatic. Whereas if one of them is antifacial, then the nodal point comes into picture. So this would be essentially a Mobius kind of a twisted cyclic transition state is what is seen here. And that corresponds to an anti-aromatic transition state. So it will be a forbidden transition state. Now let us take the example of 1,3 shift in a more detailed manner. This is a 1,3 shift and this is essentially the transition state for the 1,3 antifacial migration. Under thermal condition, 1,3 shift is symmetry forbidden in a suprafacial manner. However, 1,3 shift is symmetry allowed under antifacial manner but geometry forbidden. As I already mentioned, the 1s electron density is very small and it is unable to overlap between carbon number 1 and the carbon number 3 in an antifacial manner. So as a result of it, although Woodward-Hoffmann rule allows under the antifacial manner the migration, geometry is forbidding the reaction because effective overlap between carbon number 1 and 3 in an antifacial migration by a 1s electron density of the hydrogen is nearly impossible. So such reactions do not take place. So although the considered process is a symmetry allowed process under antifacial migration, it is rarely seen to occur in this particular case. Such a example is exemplified, such a process which is geometry forbidden is exemplified using this particular example. What you see on the right left hand side, this structure is nothing but a tautomer of toluene. So one would expect the hydrogen migration to this particular carbon through a 1,3 shift. In other words, this is a carbon hydrogen bond that is breaking. So this would be 1 and 1, 1, 2, 3. So this is a 1,3 hydrogen shift is what is expected here to go to toluene. In spite of the fact that this is a less stable structure thermodynamically in comparison to toluene structure, toluene is stable because of the gain of aromaticity energy, the delocalization energy. Such a thermal 1,3 shift does not take place quite readily, as illustrated by the example that is shown here. When this carbonate is pyrolized, the pyrolysis essentially leads to the tautomer of toluene along with small quantities of toluene, of course. How is the tautomer of toluene formed from this carbonate? The mechanism is shown here. This oxygen essentially picks up this hydrogen with a simultaneous migration and loss of the carbonic acid, which is decomposing to carbon dioxide and methanol, resulting in the formation of the tautomer of the toluene. The tautomer of the toluene under this condition is reasonably stable because it doesn't readily isomerize to toluene. So in the presence of something like tetracyanoethylene, this diene can be trapped by a Diels-Alder reaction to give the Diels-Alder effect. So this example essentially illustrates the fact that in spite of the fact the toluene is a more stable, thermodynamically stable product, it doesn't get formed under the reaction condition for the reason that this particular reaction is geometry forbidden reaction. In other words, the 1,3 shift under the antifacial migration condition does not take place quite readily because of the fact this geometry is unfavorable geometry for the overlap of the 1s hydrogen with the 1 and 3 position of the allylic system that is shown here. The most common 1,3 carbon shifts are the shifts of this particular carbon-carbon bond in a 3-2-0 bicyclic system. This is a 1-2-3, 1-2, so it is a 3-2-0 bicyclic system. In other words, it is a fused bicyclic system is what we are talking about. A fusion of a 4-membered ring with a 5-membered ring with a double bond. So this is a benzocyclopentene is what we are, sorry, this is a cyclopentene is what we are talking about. The rearrangement of that particular skeleton to 2-to-1 bicyclic system. In other words, this reaction where a fused bicyclic system undergoes a bridged rearrangement to go to the bridged bicyclic system corresponds to a 1,3 carbon shift of this kind. So you can see here when you break this carbon-carbon bond and shift this bond over here, this methylene becomes the bridging methylene. So as a result of that, you get the 2-to-1 bicyclic system. These are beautiful examples which illustrate not only the feasibility of the 1,3 shifts in an antifacial manner, the stereochemistry also revealing its nature in terms of the antifacial migration resulting in the inversion of stereochemistry. If you look at the stereochemistry of this carbon-carbon bond, the deuterium and the acetate are trans with respect to each other. And if this carbon-carbon bond is broken and if it migrates to this position, this is the product that one would get. In doing so, this is a 1,3 migration under thermal condition and it has to undergo an antifacial kind of a shift. If you see the transition state here, the hydrogen is pointing inward to the pi system and the deuterium is pointing outside the pi system. And during the course of the migration, the inversion will take place and such an inversion brings the acetate and the deuterium cis with respect to each other. So the trans stereochemistry of the starting material and the cis stereochemistry of the product between the acetate and the deuterium very clearly tells us there is an inversion that has taken place with the migrating carbon, which is this particular carbon indicated by the cursor. And the migration essentially leads to the formation of the exo deuteroacetate as it is shown. So product A is actually the Woodward-Hoffmann allowed product. Product B, where the inversion has not taken place, for example, is formed in minor quantities. That is a Woodward-Hoffmann disallowed process or forbidden process occurring in a very, very small amount, perhaps through a radical type of a non-concerted reaction mechanism may be operating under this condition to a very small extent. You can see here the AB ratio is close to 19. So A is the predominant product, not an exclusive product, which is the Woodward-Hoffmann rule allowed product. If you take the opposite diastereoisomer where the acetate and the deuterium are cis already with respect to each other, under these conditions, the inversion take place, the acetate and the deuterium becomes trans in the the bridged bicyclic system, which is the product. So you can see here the acetate and the deuterium are trans with respect to each other. This is a Woodward-Hoffmann allowed product. This is a Woodward-Hoffmann disallowed product, for example, where inversion of stereochemistry has not taken place. So the ratio essentially tells us that the Woodward-Hoffmann allowed process is the most preferred pathway in this particular system. Now in the transition state geometry for the trans isomer is shown here, which brings the hydrogen interior to the pi system, whereas for the transition state for the deuterated cis isomer brings the deuterium into the interior of the pi system. Suppose if there were to be a methyl group here instead of a hydrogen, and the methyl group would come interior to this, that would be highly sterically hindered, for example. So such a reaction will be much slower reaction compared to a reaction where you have a deuterium or a hydrogen that's being present cis to the acetate functional group. Now here is an example of a 1,3 alkyl shift that is taking place in a 6-membered ring fused to the, in other words, it is a 4-to-0 bicyclic system is what we are, fused bicyclic system undergoing a 1,3 alkyl shift. You can follow the 1,3 alkyl shift by the number. This is the bond that is being broken. So it is migrating to this position, leading to a 2-to-2 bicyclic system. In fact, this reaction is a much more facile reaction, faster reaction compared to the 2-to-1 bicyclic system. And this is the Woodward-Hoffmann rule allowed product, which is formed in 250:1 ratio. This is a forbidden product formed in extremely small amounts in this particular case. Here is an interesting example of a exomethylene cyclopropane derivative undergoing the sigmatropic rearrangement. This is a carbon-carbon bond which is undergoing the migration. The carbon-carbon bond that is broken is this particular bond. When this bond breaks, either this carbon can migrate over here or this carbon can migrate over here. Depending upon which carbon is migrating with the inversion of stereochemistry at that particular center, either of this product can be, formation can be explained. So go through this example very carefully and figure out which one of this carbon migration leads to this product and which one of the carbon migration leads to this particular product between the two carbons that are shown here. The necessary condition is that during the course of the migration, the inversion of stereochemistry of the migrating carbon should take place to lead the corresponding product. And the resulting other carbon will essentially becomes the exomethylene carbon with the specified stereochemistry that is shown in this particular case. So the process is described here mechanistically. This carbon-carbon bond is broken. The wavy line essentially shows that is a breaking bond, that is this carbon-carbon bond. So either this carbon can migrate over here or this carbon can migrate over here in the hexamethylene cyclopropane derivative that is discussed in this slide. Walk around the ring rearrangement is a very common phenomena in the case of the sigmatropic rearrangement. The reaction is essentially that this particular carbon is walking around the ring if you see it carefully. Let us say, for example, this carbon is migrating over here by breaking this carbon-carbon bond, that will result in the formation of this. Or if this carbon-carbon bond is broken and it is migrating over here, that is this carbon migrating over this, that's also a 1,3 sigmatropic rearrangement that would give this particular product. So essentially what is happening is this this particular carbon, which is the cyclopropyl carbon here, essentially migrating to the various positions of this four-membered ring, resulting in these four structures which are equilibrating structures, for example, with respect to each other. In each one of this migration, it is a 1,3 carbon shift that is taking place. If you look at carefully, the methyl group is interior to the pi system here, interior to the four-membered ring system, and the in other words, it is endo to the four-membered ring system, and the methoxycarbonyl functional group, the ester functional group, is exo to the pi system. And it remains exo throughout the course of the migration, irrespective of to which carbon it gets attached. It is exo with respect to the ester functional group and the endo with respect to the methyl group. So whenever an antifacial migration is taking place, the endo group remains endo and the exo group remains exo during the course of the migration, which corresponds to the inversion of stereochemistry, which I will clarify in a few slides later by a diagram. Now, this is a structure of a terpene. This is alpha-thugene, naturally occurring compound. This occurs in an optically pure form, for example. When you take an optically pure form of alpha-thugene and pyrolyze it at 205 degrees centigrade, it undergoes 1,3 sigmatropic rearrangement. What is the rearrangement? This carbon-carbon bond migrates over here with a concomitant migration of the pi system over here with the formation of a new carbon-carbon bond, resulting in the formation of alpha-thugene. In other words, this is a degenerate rearrangement. Alpha-thugene, if you take the plus isomer, it will produce the minus isomer. Alternatively, if we take the minus isomer, it produces the plus isomer. So during the course of the migration, essentially alpha-thugene undergoes thermal racemization process. Why is it undergoing a thermal racemization process? Because the rearranged product is an optical isomer of the starting material because of the inversion of stereochemistry that has to take place during the course of the migration. So these two are optical antipodes with respect to each other. So essentially, this is a reaction which can go back and forth because there is no difference in the energy between the forward reaction and the backward reaction, because it is a degenerate rearrangement. Therefore, the plus isomer and the minus isomer will be equally populated at certain point of the rearrangement because of the equilibrium process that is taking place. This is a very similar example. A vinyl cyclopropane is what is undergoing rearrangement to give this particular product by the migration of the carbon-carbon bond over here with the concomitant migration of the carbon-carbon sigma bond in this particular case, carbon-carbon pi bond in this particular case. Under photochemical conditions, the 1,3 hydrogen migration is a suprafacial migration, so it readily takes place, unlike the thermal migration, which is geometrically forbidden. So the photochemical 1,3 sigmatropic rearrangement is examples are given here. The hexamethylene cyclopentene cyclohexene undergo the 1,3 sigmatropic migration through a suprafacial manner of migration, and by using the deuterium labeled compound, it has been shown that there is a significant primary kinetic isotope effect. In other words, the hydrogen substituted compounds reacts 2.8 times faster than the deuterium substituted reaction. This is a primary kinetic isotope effect, which corresponds to the carbon hydrogen or the carbon deuterium bond breaking during the course of the transition state. So there is a direct evidence to show that it's a single step reaction involving the hydrogen or deuterium migration, as the case may be, which has the kinetic isotope effect, indicating that in the transition state, the carbon hydrogen or the carbon deuterium bond is breaking in this case. So what is happening in this reaction? This hydrogen, which is the allylic hydrogen, migrates to this position with the concomitant migration of the double bond, or this hydrogen here migrates to this position with a concomitant double bond migration to the ring side, for example. The migration of this particular hydrogen to give the So the methylene, the cyclopentene derivative occurs in a more predominant manner compared to the hexamethylene hydrogen migrating to this position to give this particular product. Similarly, in the case of the cyclopentadienylidene, cyclohexene, for example, the hydrogen migration from the cyclopentane to give the cyclopentene derivative is occurring in a more predominant manner compared to the cyclohexane hydrogen migrating to this position to give the secondary product. So this product is arising from the migration of this particular hydrogen, whereas this product is arising from the migration of this particular hydrogen, the two types of hydrogens that are shown in this molecule very clearly. The 1,3 superficial alkyl migration example is given here. This is a spirocyclic derivative where the starred position is a chiral center, and that is supposed to undergo migration with an inversion of stereochemistry, for example. So the migration takes, this is like, for example, the carbon migrates to this position with a concomitant formation of a carbon-oxygen double bond resulting in the formation of this particular intermediate. And then the ketoenol tautomerism essentially results in the formation of the phenolic compound, which is this particular product, which is the final product. The important point is this particular center, which has certain stereochemistry, will be inverted during the course of the migration. So this would be having the opposite stereochemistry in comparison to the stereochemistry that is shown here. Sorry, this is a photochemical migration. So this will be a superficial migration with the retention of stereochemistry. I'm sorry. The inversion of stereochemistry takes place only in the antifacial migration, which is a thermal migration. This is an example of a photochemical migration. So that is with the retention of stereochemistry, it should take place. This is a cycloisomerization of one particular terpenoid skeleton to another terpenoid skeleton. In the rest, membrane skeleton is this particular skeleton, and pseudoterrane skeleton is this particular skeleton. The migration is very clearly shown to be the breaking of this carbon-carbon bond with the migration over here, resulting in the formation of an hexamethylene compound, which is this particular. Under photochemical condition, this is a suprafacial 1,3 migration is what is taking place, resulting in the formation of this particular product. Now, the fact that the 1,3 superficial migration results in the retention of stereochemistry is very clearly illustrated by taking a optically pure isomer of this particular molecule. The R configuration of this is evident from this structure here. The migration of the acyl group to this position, in other words, the carbon-carbon bond that is broken is this bond. This has to migrate over here with a concomitant migration of this, with a ring expansion is what is taking place. A 5-membered ring, when the acyl carbon migrates over here, it adds these 2 extra carbons, so it becomes a 7-membered ring. So a fused 7-membered ring is what is being formed during the course of the migration. In doing so, this chiral center over here is retained its stereochemistry in terms of the migration being a superficial migration. So if the acyl migration were to be a simple carbon-carbon bond breaking and reattachment over here in a stepwise manner, you would expect racemization process to take place. So when the reaction is carried out under very low conversions of 21% conversion, the starting material that is recovered had essentially the same optical rotation as the starting material which was taken originally. In other words, the starting material does not undergo racemization by a simple carbon-carbon. You can imagine this carbon-carbon bond to be broken to give an acyl radical by an alpha fragmentation, which is Narish1 process. Then the Narish1 process produces a diradical. That diradical can recombine here. If that were to take place, racemization would have taken place. If it is a concerted 1,3 migration followed by the ring expansion, then the product that is formed is going to be this particular product, and the resulting unreacted starting material essentially has the same optical rotation, ruling out the possibility of a stepwise mechanism in this particular instance. Here is another acyl migration where the 2,2,2 bicyclic system undergoes acyl migration to give the fused bicyclic system in this particular case. Another example of a photochemical 1,3 sigmatropic rearrangement in this case. So let us conclude this particular module. What we have seen is the sigmatropic rearrangement is introduced in this particular module, and the terminologies used are defined in this module. Various modes of carbon and hydrogen migration are discussed. Woodward-Hoffmann rules were derived using the frontier molecular orbital method as well as the transition state aromaticity method for the 4n and 4n plus 2 electron involving systems which undergo the sigmatropic migration. several examples of the thermal 1,3 carbon shift and the photochemical 1,3 hydrogen as well as the carbon shift with the consequential stereochemical aspect of the migration is also discussed here. Wherever there is an antifacial migration, it invokes an inversion of stereochemistry of the migrating center. Wherever there is a suprafacial migration taking place, there is a retention of stereochemistry. Both the points are illustrated with suitable examples in the thermal migration of the 1,3 carbon thermal migration and the 1,3 carbon photochemical migration with the retention of stereochemistry in this particular module. Thank you very much for your kind attention. I hope you enjoyed this particular lecture.